So with chapter 6, we are going to return fully to statistics concepts, moving away from the probability. And the first chapter that we're going to start with here is on the normal distribution. Chapter 6 is devoted wholly to the normal distribution. I think I mentioned in another video that from chapter 6 on, we're going to be dealing almost exclusively with the normal distribution, which is what many people would call, what we have called a bell curve. So with that little introduction, let's get started with chapter 6 with section 6.1. Our learning objectives in 6.1 are going to be to identify the properties of a normal distribution. Okay. Identify distributions as symmetric or skewed. So this is what I said. We might see some distributions that are not normal, but what we're going to be looking at is basically determining that they're not normal. So we want to know when we look at a distribution, typically with a graph, is it symmetric, which means it looks the same on the left and the right. If you were to kind of match them up, it looks kind of the same on both sides, like a mirror image. Or if they're skewed, and we've talked about skewed before, that's where we would have most of the data here, but then we'd have some data trailing off in a tail. So this would be right skewed, and we've talked about left skewed. So we're going to talk about normal distribution curves and what they look like. So we know that discrete variables can't assume all values between two given values of the variable. For example, you could start with a sample of women, make a histogram of their heights. If we increase the sample size and decrease the class width, so maybe instead of measuring to the nearest inch, we measure to the nearest half inch, or instead of measuring to the nearest inch, we measure to the nearest centimeter, because that's a little bit smaller increment. We could change what the graph looks like a little bit. It won't change the general shape, but it will determine whether we have kind of these wide, a few wide bars, or if we have slimmer bars. And when we start to get these smaller class widths, the curve starts to look a little bit more smooth, a little bit less steppy than over here. So here, you kind of got these big 1, 2, 3, 4 steps, and over here, yes, you have steps. In fact, you have more steps, but it looks a little bit more. It looks a little bit more smooth in that step because you've got more detail filled in. Hold on, I'm trying to get this. Okay, so it looks a little bit more smooth than here, where we're missing a lot, and so that curve can't fit up against the histogram as nice. So the curve is called a normal distribution curve because it is continuous, symmetric, and bell-shaped. Now these are not entirely continuous because we have the discrete data, but an actual normal distribution curve will be, like a theoretical, will be continuous, symmetric. Theoretically, it should be perfectly symmetric. It should be unimodal. They don't talk about that right there, but it should be also unimodal, and it should be bell-shaped. So these are both what we would call approximately normal or close to normal because it's discrete data, and there's going to be gaps in between it, so it's not going to be perfectly smooth. So as I just said, those distributions, and actually really no distribution that's from real data, is going to match exactly the shape of a normal distribution curve because it's such a theoretical idea, theoretical construct. However, many continuous random variables and even some discrete random variables, so again, continuous means you can have values in between whole numbers, that there's no gaps in between the variables. But while the discrete random variables are like whole numbers or even numbers that are just to the half, sometimes we'll call those discrete, have distributions that are very close. So in those, we call them approximately normal. So if you look here, this purple curve is not perfectly normal, but it's approximately normal to our theoretical normal distribution curve. So this one would meet our criteria of it's continuous, meaning it's a nice smooth curve. We don't have any jumps or breaks. It's just a nice smooth curve all the way from top to bottom. It's unimodal, meaning it has a peak at one point and it doesn't have any other peaks. It's symmetric, meaning the left side looks the same as the right side. And what was the other thing? Missing something. Symmetric, unimodal, bell-shaped. So it's continuous, symmetric, unimodal, and bell-shaped. So that meets all those criteria. The other thing that they don't really talk about yet, but also theoretically, the bell curve would never come down and actually touch the x-axis. It would get very close to it, but it would never actually touch it. So it would just get closer and closer as you went further to the right and further to the left, but it never actually touched the x-axis. So if the probability distribution of a random variable has a graph that is continuous, bell-shaped, and symmetric, we call that a normal distribution or a normal curve. And a mathematician named Carl Friedrich Gauss determined an equation in terms of the mean and the standard deviation that describe the normal distribution curve. We're not going to talk about that formula. It's not really pertinent to the things that we're talking about in this class. But because of that, the normal distribution curve is sometimes called, and especially in the past, it was more often called the Gaussian distribution curve, from his last name, Gauss. So Gaussian distribution curve and normal distribution curve are the same thing. The appearance of the curve changes depending on what the mean and the standard deviation are. So a normal distribution is almost entirely defined by what is the mean and what is the standard deviation. And we drew these back in some other chapters, but it's been a little bit. So in this case, on the first one, we have a mean of 0. And then we have two different curves here. We have a brownish colored curve and a blue curve. And those two curves have the same mean. In other words, they're centered at the same place. Okay? They're both centered right there at 0. So they both have that mean of 0. So why is the brown curve seems to kind of end a little sooner and go a little higher in the middle? Well, that's because it has a standard deviation of 1. And so because it has a standard deviation of 1, it's more compact. It's not as spread out. And then the blue curve has a standard deviation of 2, which draws the curve out to the left and right. This will make a little bit more sense when I can, we'll have a little bit bigger graph and I'll point out the standard deviations. So this second illustration here, we have two curves that look like they're the same height. So they have the same standard deviation. In this case, both of them have a standard deviation of 2, which is like the blue curve over here on the left. Remember, this one had a standard deviation of 2. However, they don't share the same average. They don't share the same mean. And so that, even though they look like if you could slide them together, they'd be one right on top of each other, they're not located in the same place on the x-axis because the mean of the blue one is 0 and the mean of the brownish one is 2. And so the blue one is shifted left 2 from where the brown one is, or the brown one's shifted right 2 from where the blue one is. So they don't have their centers at the same place, even though their shapes, because their standard deviations are the same, are the same. So more about the theoretical normal distribution properties. As we mentioned, a normal distribution curve is going to be bell-shaped. The mean, the median, and the mode are all equal, and they're all in the center. So this spot right here in the center is going to be not only the mean, which it says here at the bottom and we talked about up above, but it's also going to be the median and the mode. So the mean is going to equal the median is going to equal the mode. All of those are going to be in the center because of it being symmetric and being unimodal. All of those are going to fall right in the center. The middle of the data, the most often of the data, and the average of the data are all going to fall right in the middle. It's unimodal, meaning it has that single peak, and there's no other place in the graph that is as high as this peak that's in the center. It is symmetric, meaning that if we could take and, fold it down the middle here along that mean, the left and the right side would fit on top of each other. Or some people like to think of it more as like a mirror. The left side is the original, and if we put a mirror up in the middle, then we'd see the right side. And it's also continuous, meaning there's no gaps in the curve. It also, as I mentioned, never touches the x-axis, although it does get closer and closer as you go to the left and the right. And then the one thing we have not mentioned at all yet is that the area under the curve is 1, or you could think of it as 100%. So the area under this curve is calculated to be, or determined to be, 100% of the data. So basically they're saying 100% of the data will fit underneath that curve. Now this empirical rule here is very important. It's shown in the graph and then explained here. And this is something that you need to remember this for the exam. I will very likely ask you on the exam between 1, 2, and 3 standard deviations, what percent of the data is there. So between plus and minus 1 standard deviation, you get 68% of the data. It's kind of like Chebyshev's, but it's not quite as complicated as Chebyshev's, because this just starts with 1. If you remember, Chebyshev started with 2. So empirical rule just starts with 1. And it's stronger because we know more about the curve, so we can say more about it or be more sure about things. If we go plus or minus 2 standard deviations, then 95% of the data is going to fall between here and here, between plus or minus 2 standard deviations. So just at 2 standard deviations, we're already up to 95% of the data. That's a lot. That's, a good majority of the data. And then if we go out just 1 more standard deviation, and it is a normal distribution curve, or approximately normal even, we should get about 99.7% of the data. So what does that mean? Well, that means that there is very little left over on these ends here. I'll put it in terms of a decimal, or a fraction rather. So if we have 99.7% that's in between minus 3 standard deviations and plus 3 standard deviations, so that would be here and here. Let me mark that with a different color so it kind of stands out. Okay, so here's minus 3 standard deviations and plus 3 standard deviations. If we have 97% or 99.7% of the data in between those two values, that doesn't leave very much left over. That only leaves 0.3% of the data outside of that. So 0.3% of the data is outside of these 2 red lines. 99.7 is between it. That leaves 0.3% outside of it. Well, remember 0.3% means 0.3 out of 100, because percent means per 100. If we shift that decimal over, then we get 3 out of 1,000. So what we're saying is, theoretically, only 3 data values would fall outside of there. And that's split between the left and the right. This is total. So that's total between this end and this end. So if we even go back and split that in half, let's say we have 0.15% on each end, then that would be 0.15 out of 100, which is 15. Shift this 2 that way, and then add 2 zeros. So that would be 15 out of 10,000 data values would fall on either the right end or the left. So just not very likely at all. You'd have to have 10,000 data values before you would anticipate that you would have only 15 of those be in the very left side tail or the right side tail of that normal curve. So just a personal example, one of my kids when they were younger, he was not gaining weight very much, and the doctor kind of kept putting me off. And at some point, he graphed it, and he showed me, or you could see from the graph, from the weight chart, that he was below the 3rd percentile. And they just kept saying, oh, he's just a slim kid, he's okay, he's fine. And I said, no, that's not okay. Like, this is very unusual. Remember, each end, there's only 15 out of 10,000. So we're saying out of 10,000 children, he was in the smallest, or the ones that weighed the 15 out of those 10,000 kids the least weight. And so I insisted that he, get checked out, and there was something wrong. I won't go into my son's business, but there was a couple different things wrong that were able to be addressed, but it wasn't, as we say in everyday language, it wasn't normal. Okay? He wasn't falling within that normal curve. So in the statistical terms or statistical phrases of it, he wasn't within the normal curve. And so it was something that needed to be looked at, because it's just very, very uncommon to be below or above 3 standard deviations. Okay, so now we're going to talk again about symmetry and skewness. We've talked about this a little bit before, but we're going to revisit it here. So we're going to look at a normal curve first, which has no skew to it. Symmetric meaning it's evenly distributed across the mean. So that means there's just as much to the left side of the mean as there is to the right side. Okay, so this would be 50% of the data would be to the right, or to the left, and 50% of the data would be to the right. If you folded it over, it would land on top of each other. No skew at all. And again, mean, median, and mode are all right in the middle. They're all equal to each other. Or if it's approximately normal, they'd be close to each other. If the majority of the data values are greater than the mean, then we say the distribution is either negatively or left skewed. So in this case, because we have this data that is tailing off to the left, remember we're always looking at the tail when we're talking about skewedness, then that data that's tailing off to the left is going to pull down the mean away from the median and the mode. The median actually ends up being in the middle, which makes sense. The mean gets pulled down, and then the mode remains above that, because that's the most often. So the median gets pulled down a little bit, and the mean gets pulled down more drastically. So for an example that you would be pretty well versed in, think about a class and their exam scores. So let's say most of the class does okay. Most of the class is, 70 to 100%, let's say. Okay. But a few people over here didn't do well. Well, what does that do to the average of the class? It brings the average of the class down. It doesn't really bring the middle of the class down, but it does bring the average of the class down. But the most often, or the most common score is still up here in, the higher range. But these few people that didn't do well on the exam pull down the mean of the class and also pull the median down a little bit. And then if we have the opposite of that, if we have the mean being pulled up positively or right skewed, then you're going to have your mean above your mode and your median. Your median's always, again, going to be in the middle because it's the median. But the most often is going to be down here to the left, and the mean is going to be up to the right. And we're always looking at the tail, so this tails off to the right, and so we call that positively or right skewed. They both mean the same thing. It's fine to use either term. This, as an example, you could think of, let me clear this off a little bit. You could think of it as income is very often described by the median because it's very often skewed. So most people, if you were to poll them or look at some sort of tax data or something, or income tax data, most people would be, within a range of values. And then you would have a very few people that would be wealthy. Okay? Well, those wealthy folks bring the overall average up. Just, a few people being extremely wealthy can pull that average up. And so if we were to give the mean, it would look like a majority of people had a higher income than they do. So you'll very often hear median used to describe the income of people because it is a little bit better representation of the data. All right, so let's look at our standard normal distribution. So our standard normal distribution, we've been talking about just normal distributions. With our normal distributions, we could have our mean anywhere because it's from the data. So if you look back here, we had mean of 0, and then here we had mean of 0, but here we had mean of 2. You could have your mean anywhere when you have a set of data. But if we're going to utilize a standard normal distribution, or if we're going to standardize it, we've all heard that term. They use it when they're talking about like the big tests that you take, whether it's SAT, the STAR test, whatever kind of, state testing or national testing. They say it's a standardized test. And you've probably always been like, okay, that's fine. What does that mean? Well, this is what it means. It means that they take the scores from that exam and take all the hundreds or thousands of students that take it, and they put it on this standard normal distribution scale. So what does that mean? Well, that means that whatever the mean is, they call it 0. So even if the mean is, let's say the mean of the exam is 72. They would treat 72 as 0. And then let's say let's draw one. Let's say you had a mean of 72, and we'll keep it simple. We'll say the standard deviation is 10. Okay. So if we had a normal curve, and the mean was 72, actually, I'm just going to leave the x-axis off because it would be a little less messy. So if we had the mean of 72, and we wanted to then mark off where 1, 2, and 3 standard deviations are, each of these would be 1 standard deviation. So if the standard deviation is 10, that would mean this would be 82. We're going to add 10. And then if we do that again, we would get 92. And then if we add that again, we would get 102. Then we could do that on the other side. trying to make these kind of symmetric, but they're not going to be perfect. And so then we would go the other way, 62, 52, and 42. And now, again, it's not always 10. It's just because in this case we had a standard deviation of 10. So this way you're going to go minus 10, minus 10, minus 10. But if we mark that, if we standardize that, we would say that 72 is 0 on our standardized scale. We would say 82 was plus 1 standard deviation. We would say, sorry, let me use the population standard deviation instead of a S. So plus 1 sigma, and then we would say 92 is plus 2 sigma, and then we would say 102 is plus 3 sigma. So instead of saying you got a score of 82, they could say you were 1 standard deviation above the mean. Instead of saying you got a score of 92, they could say you're 2 standard deviations above the mean. And then the same way on the other side. So this would be minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations. And then remember, we have those numbers. We know that if the test is standardized, and these are the numbers, then we know that 68% of the students would fall between -1 and 1 standard deviation, so between 62 and 82. So between 62 and 82, you'd have 68% of the students. And then, I'm going to run over things. Hold on a second. Let me neaten this up a little bit. Let me move our standard deviation so I can put our arrows up here. Okay. And then between 2 standard deviations, we would have 95% of the data. And then between 3 standard deviations, we would have 99.7% of the data. So 99.7% of the students would score between -3 standard deviations, which is a score of 42. And 99.7% would stay below 102, which is +3 standard deviations. So 99.7% of the data, or 99% of the students in this case, would score between 42 and 102. So almost everybody would score between 42 and 102. Most students would score here in the middle, between 62 and 82. A good majority would fall between 52 and 92. And then almost everybody would fall between 42 and 102. Now, that doesn't mean a student couldn't get above one of those if it was, theoretically, if it was actually possible, if the scores actually went that high. But 99.7, almost all of them would be between that -3 standard deviations and that +3 standard deviations. So what we need to do when we're working with normalized data is we need to be able to figure out, when we're given a value, what the z-score is. And the z-score is not anything, like, it's not big and confusing. The z-score is just the number of standard deviations from the mean. So in this case, if somebody had scored a 92, their z-score would be +2, because they're 2 standard deviations above average. But we don't want to have to draw it every time. And so the calculation would get it. So let's use that for this calculation. So in this case, the student got a 92. If we subtract the mean, which was 72, and we divided that by the standard deviation, which was 10, on the top we get 20, divide by 10, and we get 2. So you can see it on the graph, and you can see that the formula gets us the same thing. So you take whatever the student scored, or whatever the data is, take whatever value you're looking at, subtract the mean from that. That'll tell you whether you're above or below and by how much. So in this case, the student was 20 points above the average. And then we divide that by 10, and you say, oh, well, if you're 20 points above the average and every 10 points is a standard deviation, then you're 2 standard deviations above the average. Let's do one more. Let's do one that's below average. Okay. So let's say a student, and we'll pull one that's doesn't fall right on it. Let's say a student scored 55. Okay. So they weren't quite to -2 standard deviations, but they were below 1 standard deviation. So what would we do for the z-score? Well, we would take 55 minus 72, and then we would divide that by 10, because we're interested in a score of 55. The average is 72, and we're going to divide that by 10. And so on the top, if you take 72 minus 55, or sorry, the other way around, 55 minus 72, we're going to get a -17. Well, what does that -17 mean? That means they scored 17 points below the mean, 17 points below the average. If we divide that by 10, that's going to get us -1.7 for our z-score, because they're -1.7 standard deviations below the mean. So again, not quite to 2, because they weren't at 55, but but lower than a 62. So that's how we calculate the z-score. And if we want to find the area under the standard curve, we can look at there's various different ways to do this. Some calculators will do this. There's computer programs that will do this, but we're going to stick with just using the textbook information, the textbook method, because it's accessible to everybody. So if we want to know what the area to the left of a certain z-score is, in other words, for the test scores, what percentage of students were at a certain score or below, we can use the chart that's on your important formulas and tables. So we've only used the formula so far for chapter 1 through 5, but now in chapter 6 we're going to start using 2 tables very, very often. Let me pull them up. Okay, so we again had only used for chapter 3, 4, and 5 had only used the formulas that are here. But now for chapter 6 we do need the formula for the z-score, but in order to get that percentage, or that area that's to the left of a certain z-value, we need to go down to what's often called the z-table. The z-table, or the standard normal distribution table. And if we go down and we say, the example they said was, what if you were at a z-score, or what if you had a z-score of 1.39, what percent of the data would be below that? Well, we go over here, and I'm on the wrong page right now because I've got a positive value. So if our z is 1.39, that's a positive value, which means we're going to have to be looking on the positive part of the chart. So we need to go to the second page. So on the second page, you'll find 1.3. Okay. So here's 1.3. And then if we go up to the side here, we want to go over to 9 because we want 1.39. So the left side gets us our whole number and our 10th place, and then the top column, the columns give us our 100th place. Okay, so now if we match those up and we go from 1.3 to the 9, so 1.39, we're going to end up over here with 9.9177 as our value. Now, a couple things I want to point out. I'm going to draw a picture of that so you can see it a little bit better too. A couple things I want to point out. You notice on the chart it has this same picture that you're seeing at the top of our slide. So it says this chart gives us the area to the left of a Z. So we can see the blue shaded in there. And if we go to the other side, it does the same thing. Just in this case, all the ones on this page are positive Z values, so they're to the right of the 0, but it's still the area to the left of that Z. Okay? So it has that picture on there. And let me make this picture for this particular problem. Let's do a visual for this. So what they're saying is, if you had a Z-score that after you calculated it, so you did your Z equals X minus mu over sigma, whatever those values were, and when you got done with that, you got 1.39. So 1.39 is up here. This doesn't have to be a perfect picture, it's just to help you visualize it. So there's 1.39, and we want to know what percentage of the data or what area under the curve is to the left of that. So we want to know how much is down here. If we're thinking of it as the test scores, you're saying what percentage of the students excuse me, scored less than 1.39 standard deviations. And then when we go to the chart, and then when we went to the chart, here's a little shortened version of it. We came down to 1.3, then we went over from there, and we went from 0.09 at the top, and we came down, and we got that 0.9177. So we're saying that from here all the way down is 91.77% of the data. 91.77% of the students, if we were thinking of our other problem. So a good majority, over 90%, are from 1.3 standard deviations and below. And we can look that up on the chart. So sometimes when you're trying to calculate values, instead of knowing how much data is below that, you might want to know how much data is above that. So you might want to, with our example, know what percentage of the students scored above 1.39 standard deviations. So if we want to do that, when you're looking at the curve, let's go back up to the one that we just did. If you're looking at the curve, if 91.77% of the data is to the left, then that means over here is the rest of it. Well, remember that together it has to make 100%. So to get to the right side, we'd have to take 100% minus the 91.7% that was to the left. So if we did 100 minus 91.77, we're going to get 8.23. So 8.23% of the data is to the right. So if you want to get to the right of a certain value, and you might hear the terms, if you were talking less than, they might use the terms below, under, no more than, something like that. They might say, we want to find the percentage or the probability that you're under that, below that, no more than this. That would all indicate this to the left with the 91.77. But if instead they said, we want to know above that, over that, at least as, so at least 1.39 standard deviations, that would mean we're going to the right, and so you'd have to use this other method. We'll summarize this when we get through a couple examples. So in this case, they're giving us another value. They're saying, what if we wanted to know the area under the standard normal distribution curve? Oh, and remember, if you're talking in decimals, 100% is 1. So in this case, we have a Z of negative 1.09. So again, it was calculated. Somebody calculated the values. They knew the x and the mu and the sigma, and when they were all done with that, they got negative 1.09. And then the question is, what percent of the data falls above 1.09? So that would be up here. You can see it's less than half because it's above the mean. But if we go to the chart, remember the chart, oh, I drew that wrong. Hold on a second. It's negative 1.09, so it's on this side. So negative 1.09. Okay, but we still want above that. So it's going to be more than 50% because we're going across the center. So if we go to our chart, we're still going to look up negative 1.09. So we're going to be on the negative side of the scale, or of the page. And here's negative 10. Okay. So that's our value that we're going to use for our row. And then 9 again. I don't know why they keep giving us 9s, but you could have any value, but they gave us a 9 again. And then we're going to follow that across. And if we go 1.09, we're going to meet up with 0.1379. But remember, that's the value to the left. So to the left is 0.1379. So this part here is 0.1379. But we don't want that part. We want to know what's over here. And so what we're going to do to get what's over here is we're going to say 1 minus 0.1379. And that's going to give us the rest of it. So 1 minus the 0.1379 comes out to be 0.8621. Let's do it with percentages because I think it sets with people's brains a little bit better. So what we just said, we looked up on the chart, and the chart told us that over here was 13.79% of the data. So we subtracted that from 1, and we found that that means that over here there is 86.21% of the data. And that's what we wanted. So 0.8621 or 86.21%. So 0.8621 is the area. It's the percent of data that's up there. It's the probability that someone would be in that area. They all mean, not necessarily mean the same thing, but they all produce the same thing, the same number. Okay, so last but not least, we're going to go to what do we do if we have two z-values and we want to know the likelihood that a score or that a value is in between those. So let's summarize what we have. So we said if it asks to the left, below, less than, under, we can just use the chart. If it's to the right, then we have to do 1 minus whatever's on the chart. And now we're going to have a third thing where it says between. These are the only three. And we're going to do this basically the whole rest of the chapter. So if you can kind of get this set in your brain for this first section, then we're just going to kind of do a lot of the same for the rest of the chapter. So for between, we're going to take two different chart values. So we're going to find chart value 2 and we're going to subtract chart value 1. So we're going to take the two data values. The largest data value we'll call the second value. The smaller one we'll call the 1. And we'll find both of those and then subtract them. You can't subtract them before you go to the chart. You have to go to the chart, get the two different values, and then subtract them. It will not get you the same answer at all if you try to subtract them first. So let's look at this data about this particular example. Now this one, they did give us a picture. So we've got, it says we're between 1.43 and negative 1.87. So again, the z-values were calculated. We got a z-value of 1.43, a z-value of negative 1.87. And we want to know what is the area between those. Okay, so let's go to our chart. Let's see if I can clear this. How do I clear this? Probably another way to do it, but I'll just do it this way. Okay, so if we go to the chart and we look up, again, the larger value, it doesn't matter really which one you look up first, but I'll just look up the bigger one first because it'll help me explain it better. So we're going to go to 1.4. Okay, and then we want 3. So that's this column right here. Then we're going to take and follow it in and down. So 1.4, 3 gets us right here. So our value for the 1.43 is 9236. So let's write that down. So 1.43 from the chart gives us 0.9236. Try to avoid using an equal sign between those because that doesn't equal 0.9236, but on the chart it gives us. So a z-value of 1.43 gives us 0.9236 on the chart. Now what does that mean? Well, that means that the area from here left, all of this area, not just the shaded area, but all this area is 92.36%. So all this area is the 92.36%. But we don't want all that area. We want to cut off or take out the area that's from 1.87 down. So we want to take the area that we found with the 1.43 and we want to take out the part that's down here. Okay, so if I take the blue area and I subtract the red area, then I'll have the original shaded area that I wanted that was just between these two. So if I take the blue area, subtract off the red area, I'll get what I want. So if we go back to the chart, we have to look up negative 1.87. So I'm going to go to the other page. Negative 1.87. Whoops. Okay, and then we're going to follow that over negative 1.87 is going to meet right here at 0.0307. So there's only a little bit more than 3% of the data that's below that negative 1.87. Okay. So the z-value of negative 1.87 when we went to the chart got us 0.0307. So now what we want to do is we want to subtract those because we want to take the whole area that we had from this one and subtract off the little bit that's to the left of that one. So 0.9236 minus 0.0307, and that will get us 0.8929. And so in this area that we were interested in, from here to here is 89.29% of the data. Okay, from here all the way down was 92%, but we took off the little bit that was from here to here that was about 3%, and we ended up with 89.29%. Okay, so these are the only three things that can happen. They can either ask to the left, they can ask to the right, or they can ask between. If they ask to the left, that's the easiest one. You just go to the chart and you got it. If they ask to the right of a z-value, you go to the chart, but you have to subtract that from 1 because you want to be on the right half, not the left half that the chart gives you. And then if they ask you between, you have to take the bigger value off the chart, subtract the smaller value off the chart, and that'll get the remaining bit in between. Okay, so we've got, yes, I thought we were kind of getting close to the end. Okay, so we've got 3 slides left, just a couple more examples. So it says here that the area under the standard normal curve corresponds to the probability that the corresponding random variable falls within a certain range of values. So I've kind of been using it already, the probability. So it says, for example, if we look up z equals 1.73 on the table, we see that 0.9582 of the area is left of this value. So what does that mean? That means that the probability that your z value falls under 1.73 is going to be whatever you find on the chart value. Remember, less than is left, less than, under, below, those are all going to be to the left. And so if we go to the chart and we look up the 1.73, we've got 1.73, and if we go in and over 1.73, that gets us 95.9582. And so that means that the probability that a z-score is below 1.73 is 95.9582 or 95.82%. They do mention here too that saying below or less than or equal to 1.73 would get you the exact same answer. And the reason is because all that you add when you say less than or equal is you add the vertical line that's right at 1.73, and a vertical line segment, lines don't have any width, so they don't have any area. So whether you are including 1.73 or you're not including 1.73, statistically you still have the same value. So some books will use less than or equal, some books will use less than. You get the exact same answer. Don't worry about that. That doesn't matter. Okay, so let's look at another example. Now this one says we're going to do the probability between two values. I'm going to write this again. I know we just did it, but I'll say it again. If they ask to the left, we're just going to use the chart. That's what we did on the last problem. If they ask to the right or above or higher, that's going to be 1 minus whatever's on the chart. In this case, they're asking us a between, and so we're going to have to find a chart value for the larger number, and then we're going to find the chart value from the smaller number, and we're going to subtract them. Okay, so what do we have here? They want to know the probability that we're between 0 and 2.53. So the larger value is 2.53. So let's look at the chart for what we get for 2.53. Okay, so 2, gotta go down a little bit, 2.53. Got stuck on point 3s and 9s for the last digit. Okay, so we got 0.9943 for our first value. 0.9943. Now let's do the second value. In this case, the second value is 0. Now you might already realize that below 0 is going to be 50%. But if you didn't realize that or think about it, let me show you where you find that on the chart. So if you're looking on the chart and you need to find a z-value of 0, there's 2 different places you can look. They actually kind of overlap them between the positive page and the negative page. So over here, they call it negative 0.00, which 0 doesn't have positive or negative, so it doesn't really matter. But negative 0.00, they say it's 50%. Also over here, 0.00, so we got 0 here, and we've got 0 here. We also get 50%. So it is on the chart. It's right in the middle. In fact, it's on both of the pages. So the z-value, or the amount of area that's below 0 is 50%. And so we're going to subtract those because we're doing a between. So take chart 2 minus chart 1. So 0.9943. Ooh, that looks horrible. Give me a second. 9943 minus 0.5000 gets us 0.4943. In other words, 40 between here and here is 49.43% of the data is from the mean right there in the middle at 0 up to 2.5 standard deviations. And the last thing we're going to do for section 3.1, and then we'll call it a break for this video, we'll stop this video, continue on to the next one, is we're going to talk about finding a z-value for a specific probability. So in other words, don't know if any of you are game show fans, but we're kind of playing Jeopardy. They're going to give us the answer, and from that answer, we're going to try to figure out what was the question. So instead of giving us a z and asking us the probability, they're going to give us the probability, and we're going to try to find the z-value. Okay? So let's look at the situation that we have here. Again, we're going from a 0, and then we're going up to a z-value. So it's kind of like the last problem where we had 0 as one of our values. So they want to know what's the probability that we're between 0 and some z-value. Or not what's the probability, they're going to give us the probability. So they're saying between that 0 and that z is 0.2123. So we know that between those two, we get 0.2123. So in this case, if they do betweens, they can only do it from 0 to a z. They can't do it between 2 random z's for this type of problem where we're working it backwards. So if we had, we know that from here down is 50%. So if this is 50%, if this is 0.5000, then to get up to here, all of this must be 0.7123 because we know that that little shaded in area is our 0.2123, and we know from here down is 0.5000. So together from here down must be 0.7123. Why is that important? Because that's what we need to look up on the chart. We need to know the area that is less than, so we want to know the probability that a z is less than 0.7123. So we need to know what z do we need so that below that I get 0.7123. So now we go to the chart, and on the chart we're working backwards, remember. And so on the chart we need to not look out at the columns, like the margins. We're not going to look at the left margin and the top margin. We're going to look inside what I call the body of the chart. So we're going to look in this area. And we're going to try to find as close as we can to 0.7123. As close as we can. Now in this case, they were nice and gave us one that falls exactly. It doesn't always do that. Okay? So in this case, we've got 0.7123 right here. So we go from there. Remember, they gave us the answer. We're going to go back and try to find what was the question. Well, the z value, the question, must have been .56. So 0.5 and then 6 is our hundredth spot. So our answer is 0.56. So we just figured out that that z value right there must have been 0.56. Now, I want to tell you something real specific about this. I will not ask one of these on the test. I won't ask you one of the backwards ones. I won't give you a percentage and ask you to find the z value, but it will be on the homework. Just a couple probably. Most of them will be the other type, but there'll be one or two maybe where you have to work backwards, where you're given a percent and you have to find the z value. So here's our example of that. Let me do one more of these because I just don't feel like that's quite enough. Let's do one. Let's say they said you have an area and we want to know, we have a z value, and this area right here is 0.3588. I'm just grabbing something. I don't know how great this is going to be on the chart. But we want to know what z value would give us a percentage of 0.3588. Now this one is easier because this one is already set up with a z and below. It's not a between one like the last one. So this one we already know that it's 0.3588. So we're going to grab our chart, and again we're going to look at the body of it because we're working backwards. We've got the percentage and we're trying to find the z. So we're going to find our as close as we can. What was the value? 3588. So as close as we can to 3588. So here's 3557, 3594. We wanted 3588. So that looks like it's the closest one. Okay, so it looks like 3594 is the closest we can get. So you just get as close as you get. We got the 0.35. We're a little higher than 88 on the end, but that's closer to 94 than it would have been to the 57. Okay? So it's closer to the one that I circled than this one on the right. Then we're going to go from there and we're going to go over, and we get negative 0.3, go up, 6. So negative 0.36 is our z value. So z equals negative forgot already. What was it? Negative 0.36. Okay, so you would need a z-value of negative 0.36 to have 35.88% of the data below that z-value. And then you could also have one that was to the right. So if they gave you a problem like this and it said, what's the probability that, or what's the z-value that would give us a area to the right, or a probability of being to the right of 0.4875. Okay. Now this is close to what we want on the chart, but it's still giving us to the right, not to the left. The chart gives us to the left. So for this one, we're going to have to look, what does that leave us from here down? So if we take 1 minus 0.4875, we're going to get 0.5125. So what I need to look up on the chart, in the body of the chart, is the 0.5125. There are other ways to use the chart than what I'm explaining, but I just like to stick to one method. So if you come up with a little bit different method, the chart is all symmetric, so there are some other ways that some people like to use it, but I'm going to try to stick with this, just the one method. Okay, so we need to find in the body of the chart, as close as we can to 0.5125. Okay, so I've got .5120, I think is the biggest one, or the closest one. 5160 would be further away, 5080 would be further away, you got 5120. So if I go over and up, I've got 0.03. So my z-value is 0.03. Okay, so there's the three different kinds. The first one was a between. Remember, with this type, if it's between, they have to give you 0 because otherwise you wouldn't know where it was placed. So they could have between 0 and a z-value. That was our first one that we did here. They could have a z that's on that has we want the area to the left of it, or they give you the area to the left of it, or they could give you where you're trying to find a z and they've given you the area to the right of it. So there's an example for each of those if you need to come back and rewatch or look at your notes. I will see you back for section 6-2.